So now we'll do question 1b. That is, prove that if I is a finite set, then the intersection of the UIs is open. So in other words, show that the finite intersection of open sets remains open. Let's do it here. So we consider I to be a finite set. We let W be the intersection of the UIs. So we have two cases. Case 1, W is an empty set. In this case, we trivially accept that W is open. Without any issue, we just accept it. Empty set is always open. It's also always closed. Case 2, W is non-empty. And this is the case that will require all the work. So let X be inside W. What is it we want to do? What we want to do is to show X is inside the interior of W. So that way W will be open. So we recall W is the intersection of all the UIs. So W is an intersection of all the UIs, so then X is an element of UI for all I. And we recall the UIs are open. They're open subsets of Rn. So if X is an element of UI and UI is open, then it's inside the interior. So if inside the interior there is a radius such that the ball of radius Ri around X is contained in UI, or contained by UI. So our goal is to show X is in the interior. And the way to do that is we want to find a radius R strictly greater than 0 such that the ball of radius R around X is contained by W. Well, we know W is the intersection of all the UIs. So this is our goal, find a radius that does this. Okay. We could see that this is equivalent to saying the ball of radius R around X is contained by all the UIs individually because it's contained by the intersection. So in other words, find radius R is strictly greater than 0 such that the ball is contained by UI for all I. That's what we need to do. And it's important to know that this radius, this R, has to work for all I. It's their existent R for all I. Okay. So how is it we do that? Here this time we just pick R to be the minimum of the Ri's. And I want us to observe something. Number 1, I want us to observe that the radius, the minimum of these Ri's, is strictly greater than 0. And that is because I is a finite set. There are only so many elements greater than 0. The minimum of them will still be greater than 0. That's number 1. Number 2, I want us to observe that the ball of radius R centered at X is contained by the ball of radius Ri, which is just contained by UI for all I and I. So this subset is from before, so that's for free. Why do we have this subset? Why? We have that subset because R is the minimum of all the Ri's. So R is less than or equal to Ri for all I and I. That's why. So think of it this way. We have X and you have a radius R. In the second case here, you have the same x, but your radius either stayed the same or got larger. So if your radius stayed the same or got larger, then it stands to reason that you're covering more elements. You're covering everything from before and maybe more. Right, so this is blue, this is the blue ball, and this is the red ball. So at that point, we're pretty much done because then the ball will be contained inside the intersection of all the UIs. And that's just equal to W. So therefore, X belongs to the interior of W. X was picked arbitrarily, therefore W is open. Before I continue, I want to point out why is that we need I to be a finite set. This is important because if I was an infinite set, this proof would not work. It was not guaranteed to work, at least. So aside, why is I a finite set? Why not an infinite set? If I was infinite, then this definition here doesn't make sense. And this doesn't make sense. The minimum, you can't take a minimum. Can't always take a minimum. Instead, what you could do is you could take an infimum. You could take an infimum like this. So you might wonder, why not just define R to be the infimum? So why not like this? Well, this poses another problem, because how do you know the radius is still strictly greater than 0? For example, what happens if the infimum was like this? What happens if your Ri is equal to this and it's an infinite set and it just goes on forever? This infimum is 0. So if R is equal to 0, this is a problem. Because R needs to be strictly greater than 0. So for these reasons, you cannot assume, you cannot say is open. You cannot assume this is open when I is infinite. You cannot assume. Assume is a better choice of words. Let's use red there. You cannot assume that the infinite intersection is open. But what you can assume, however, that the intersection of the UIs is open when I is finite. So that's what question 1b is trying to say. The finite intersection of open sets remains an open set. And that's it for 1b.